100? Sure. That's the only requirement, is that the area is 100. Would this have a certain perimeter? What would the perimeter of this be? 202, right, feet? Okay, could x be bigger than 100? Yeah. Yes. Could I do 200 and then a half? Wouldn't the area of that still be 100? Yeah. Could I do 400? 800? 1,000? A million? Right? Theoretically, I could go as far as I want. The point is what? It's not closed interval. What? Yes, yes, but we've changed the problem. It's now, we've switched. We no longer have a restriction of how much fence. We have a restriction of how much area we need to have. Okay, so we can't use the closed interval method. We cannot. Right? It's not a closed interval. So that means I'm going to need to do what? Open interval, which means find the local max and mins, right? So we're going to take the derivative of this function. All right, derivative of 2x. 2. What's the derivative of 200 over x? That's really what that means, right? Bring the x up, x to negative 1, do your power rule here. So what would that be? Negative 200, x to the negative 2, drop that back down. So negative 200 over x squared. Yes? That's our derivative. Could you do that? Oh yeah, you could have done quotient rule, but you know, I think that's better because you're just using power rule. All right, what do we do with the derivative? Find the critical numbers. Figure out where it's 0, figure out where it's undefined. Okay, p prime equals 0. All right, we have to figure out where that derivative is 0. How are you going to do that? Set it to 0, yes. And then to do that, there's a couple of ways you can do this.
Divide it by 2.
You want to divide everything by 2? That's fair. I'll do that. You want to divide that by 2, it's 1. Divide that by 2, it's 100 over x squared now? Okay with that.
Just find a common denominator.
You could do common denominator. You'd need what, x squared, x squared? So that would become x squared minus 100 over x squared equals 0. And a fraction can only be 0 if the top's 0. So now this becomes x squared minus 100 equals 0. Move the 100 over to the other side. Square root both sides. You get 2 answers, right? Plus or minus 10? Plus or minus 10. We're only going to take the plus, right? Because our domain is positive numbers. So from here, x is 10. That is one critical number. Now, is there anywhere where the derivative doesn't exist?
0.
At 0, right? But 0 is not in the domain.
So nothing.
Nothing from there. So we only have one critical number. Got it?
Do we technically have to still plug it in?
Pardon me?
Do we technically still have to plug it in?
Plug what in?
X? Or
This?
the critical number? Yeah, since we only have one.
Plug it into what?
Derivative.
No. What are the things that get plugged into derivatives? Not critical numbers, test points. See, this is, I mean, look, this is the most confusing thing the students have with this whole idea is like, when are you plugging that into that? When are you plugging into this? You got to get that squared away in your mind. We're doing the open interval method, so we're going to get critical numbers. We're going to draw a number line. We're going to pick test points. Those are going to go into the damn derivative. All right? So let me go ahead and do that. Draw you a quick little number line. I'm kind of running out of space here. Draw a number line. Here's 10. And I'm going to put 0 here, and remember there's nothing over here, right? That is right. Right? Test points. What do you want? 5 and
15.
15. Okay, and where are those going? Into the damn derivative. Where's the damn derivative? Right here. Let's plug 5 into this. 5 squared.
25.
200 divided by 25.
4. I'm just kidding.
8. Okay, 2 minus 8. Negative number, right? Negative number.
Yes.
What does that mean my perimeter function is doing over here? It's going down. My perimeter function's going down. What are we trying to find? The minimum value of P. Right now it's going down. If it goes back up, we've got the minimum, don't we? So we plug in 15, plug it in here, whatever, you're going to get a positive number. It goes up. It's what? 225? Oh, squared. Yeah. Yeah, so 200 divided by, that number is going to be smaller than 1. 2 minus that number is going to be a positive number. So what have we found? Local minimum. But it's the only minimum. Because we're saying that the perimeter function goes down, then back up. That means it never comes back down and goes back up, right? We have found the lowest point.
Does that make it global?
It's the global, yes. So now we need to, write the answer here. We have a minimum P at x equals 10. And y equals what? I know we have a minimum value of perimeter when x is 10. What's y? How do you get that? Right there. Your constraint will always allow you to solve for that other variable. So I go there, 100 divided by 10 is 10. So it's a square again. 10 by 10. You build me a 10 by 10 square, it will have an area of 100, and you will have used the least amount of material to make the outside. You will have a perimeter of what, 40? 10, 20, 30, 40. There's no other way to build a rectangle to have an area of 100 with a smaller perimeter. That's it, that's the best. Understand? These are basic problems because I really wanted you to see this because I wanted you to see the difference between closed interval and open interval and how you have to attack it different. Okay?
What about the cosine?
That's, yeah, we're getting to it. Question?
This is going to be on our test.
This will not be on the test on Tuesday. Yeah, this will not. Everything we did in terms of like concavity, concave up, concave down, inflection, that's all fair game on the test.
So everything before this class?
Before this class, yes.
Did you put the review up yet?
I know, every time I've sat down to do the review, I've thought to myself, do they really need a review?
Yes.
Yes.
How you saying that?
Yeah.
I know, but that's the thing. I don't know how to. Okay, let's continue. Let me see how much time I have.
Let's just jump into the deep part. Let's just do whatever it is. The soda can.
A can must hold 1 liter. That's 1,000 cubic centimeters. We're going to use 1,000 cubic centimeters as our unit here of measurement. Find the dimensions of such a can with the smallest surface area. So I have an image here. Let me see if I can make this all fit together. Yeah, okay, there we go. Do y'all see this little soda can here? It's a cylinder, okay? It's a right cylinder. And what I can do here is I can change the radius of it and make it smaller, taller, okay? And what I want you to notice is that the way I have the computer set, it's gonna keep It's going to keep the volume always 1,000 cubic centimeters. So it's always going to hold 1 liter. But keep your eye on the surface area. Watch what happens to the surface area. If I make a really tall can, really tall, narrow can, look at how much surface area I'm using. That's a lot of aluminum, right, to make that can? Or I can go the other way and make it really, really short and wide, like that, and look at the surface area, 1,700.
It's just a cap.
Is there some, where is it the best? 600, 550, 553, somewhere around 553, I think. Yeah, somewhere around there?
Yeah.
Okay, so somewhere in here is the optimum way to do it, so that we get the least amount of surface area. So find the dimensions of such a can with the smallest surface area. Got it? Objective.
Find the smallest surface area.
Smallest surface area. I'm going to say minimize. Minimize surface area of a can, right? We want to minimize the surface area of a can. We should draw a can, shouldn't we?
Sure.
Okay, so here's my can.
Kind of tall.
Thank you. It's a Red Bull. Red Bull can. All right, aren't we going to need to write the formula for the surface area? What is the surface area of a can?
R squared.
Pi r squared times.
Pi r squared times h. So that's a formula in our formula sheets, yes?
Yes.
Okay, so think about that formula. It's pi r squared h. Pi r squared h. Now we have to label some things on our can. The radius, the r is halfway, right?
Oh, no, that's fine.
And the h is, are you changing your mind?
Yeah,
Okay, that's volume.
yeah. But
That's all right. There's a formula for it, no? There's no formula?
Pretty serious.
No surface area.
No, we're not going to do that. You're not doing that. Stop. Man, I have all of y'all's papers, graded stuff. I keep forgetting to hand it back. Please, at the end of class, just come up and grab all your stuff out of here. So look, let's say we have a can, all right?
It is R squared.
That's the volume.
Was it like 3/4 something?
Don't look it up.
I didn't.
Here's our can. Here's our can, right? We want to know how much material there is on the outside of it. How about the top? What is the top? A circle? What's the area of a circle? Pi r squared, right? Pi r squared for the area, right? So shouldn't the top area of the can and the bottom of the area of the can each be pi r squared? So that we should have 2 of the pi r squareds, yeah? You good with that? Now, I'm going to take our can, and I'm going to cut it down the side, and I'm going to lay it open like this. What do you see? A rectangle. Do you know how tall it is?
H.
H. Do you know how long this is?
The radius.
Close. It's the circumference of this thing, isn't it? Right? I laid it open. What's the circumference of a circle?
2 pi r?
2 pi r. Very good. So this is 2 pi r. So the area of this laid open is 2 pi r, which was the circumference, times the height. So plus 2 pi r h. There we go. See, we didn't need a formula sheet. We didn't need Siri or Alexa or anyone else. Okay? That is the surface area of a right cylinder.
Right cylinder?
Well, you can have a cylinder that looks like this. That's skewed off. Right means that this angle right here is a right angle right there, straight.
What would the essay be like?
That's a different story. Yeah, that's a different, that would be a harder thing to just spew out. I'd need to know the angle, and then, right, you would have to have like what the offset is, and you could do it. It's just not as simple as this. Okay, that's the thing we're trying to find the minimum of, right? It contains two letters, R and H. We need it to be in terms of all R's or all H's, a single variable. What have we not put up here yet? This is our objective, right?
The constraint.
This is our objective, right? The constraint. Okay, can this can be any can we want? Is there some sort of restriction on it?
Volume of 1,000.
The volume has to be 1 liter or 1,000 cubic centimeters, right? So we're going to measure everything in centimeters in this problem. That's our constraint, right? But we know the formula for volume. It's the area of the top piece, right, pi r squared, times how deep it is, h. So this formula is pi r squared h equals 1,000. This is the third problem we've done. Are you starting to get a flavor for like what's happening here? You set up the objective, draw some pictures, figure out what the constraint is, try and get this down to one variable. That's where you're going to solve for one of the variables. So do you want to solve for R or H over there? What looks easier to you? H, definitely, right? Because if we solve for R, we're going to do a square root. So let's solve for H over here. H will be 1,000 over pi r squared. There's just no way around that. That's what we have. Now I'm going to come back to surface area. What's that? And just for convenience, I'm going to start calling this A instead of SA for surface area. I'm just going to call that A, and then this is, I'm replacing all of my what's here? What am I replacing? The H's with that. 1,000 over pi r squared. Check that out. That is a new equation that has just r's on the right-hand side. So I can look at the area now as being a function of the variable r.
What about the other R, by R?
I'm just saying there's r's and just r's. There's no h's anymore.
Oh, here's the R.
Oh, yes, thank you, yes. I forgot that r. Ooh, that would have caused problems later. 1,000 over pi r squared. There we go. We're going to just clean up first. There's a few things that clean up. 2 pi r squared. Okay, let's see. One of these r's cancels, and the pi's are gone completely, right? So we just get 2,000 on top and an r on the bottom. Plus 2,000 over r. This is our somewhat clean objective function.
Can we divide by 2?
No, not yet. If we set things to 0, we can, but we need derivatives first, right? What's the next step? We have the objective function.
Now take the derivative.
Domain. Is it open or closed, right? What are you going to do? So look, let's sketch this out. I've never done this before. If we're going to set up like a set of steps on how we're doing this, the first thing we're doing is we're what? What are we doing? Objective. Okay, so you figure out what the objective is. Maybe you do some pictures or something. I don't know. Constraint. Fourth would be turn your equation into a function, right? One variable. Does that make sense to you? Start out with your objective equation, basically. Draw some pictures, use your constraint. Then from that, you'll come up and you'll turn your equation into a function of one variable. And then domain, right? Domain, that's going to determine, are you going to do closed interval or are you going to go down the open interval path, right?
The damn domain.
The damn domain. We better not use damn. We need another word for
The dang domain.
dang.
Gosh, darn, yeah.
All right, so let's think about R. What are our restrictions on R?
No.
Radius of this can. Can it be 0?
No.
No, look at the height. Your height depends on the radius, right?
Yes.
And if your radius is 0, your height is undefined.
Could be
So it could be anything all the way up to 0. 0 to infinity again. You could make this thing as wide as you ever wanted to. It would just be really, really short. This is theoretical, right? We're going to find an optimum solution here, but we need the domain to dictate which method we use.
So open.
Open. So we're going to do derivative, critical numbers, number line, test points, up, down, up, all that stuff, right? That's the procedure.
You take derivative for both though, right?
Yes.
So you could have just taken the derivative already.
Sure.
But you could have.
Yep. The only danger in that is you forget that you needed a domain at some point, right? So I always like to look at the function before I take a derivative and figure out which method I'm using. But you're going to need derivative either way. It's just what you do with that. So what, 4 pi r? And then this one is very much like the last one we did, where we had 100 over x. So this should turn out to be negative 2,000 over r squared. Right, because that's really r to the negative 1. Then you bring the negative 1 out, subtract 1. There's our derivative. Beautiful, beautiful.
So when because you took derivative of 2000 over r, right?
Yes.
So is it safe to assume that you can just increase the power if the variable is by itself on the denominator?
Well, what if it was r squared down there? Are you saying would it turn into like negative 2,000 over r cubed?
Yeah.
No, it wouldn't. No, because it would come up as an r to the negative 2, then the negative 2 would come out, and that would change that to a negative 4,000.
Oh, okay, I see.
Can you write out like the top times the derivative at the bottom minus? I just want to see it.
Quotient rule?
Yeah.
You want me to do a quotient rule on this?
Yes. I just want
Okay, derivative of the top. What's derivative of the top?
0,
Times the bottom?
1,
Nope, not derivative of the bottom.
2 to 2.
No. We're doing derivative of that, right? Derivative of the top is 0 times the bottom minus derivative of the bottom is derivative of r.
Yeah.
Okay.
Good question.
I got it. So that's 1
1
times
times 2,000 over bottom squared.
Yeah. Okay, I just wanted to see it.
Gone, negative 2,000 over r squared. That's the quotient rule, gets you the same result.
So if R was to the power of anything, you just do the quotient rule, right?
No. 2,000 over r, that derivative, I'm doing this. I'm moving the r up as an r to the negative 1. And then I'm taking the derivative.
So you're saying if R was like R cubed?
I would move it up, and it would be r to the negative 3. And then I would bring the negative 3 out and make it negative 6,000 r to the negative 4.
Oh, okay.
Right? I think that's cleaner than quotient rule.